what I'm going to do is use this definition of the controlled U. I'm going to substitute in this decomposition. And I'm going to use this principle iteratively, right? Because we'll have more than 2 operators. But hopefully you can see if I had 3 here, then it would hold as well. And how many do we have? 5 total here, and 6 if you count the global phase gate. So let's state the following theorem, which is just coming from these 3 results. I'm going to have the theorem that in a circuit controlled, any single qubit unitary U will be equal to, I'm going to use this decomposition, and I'm going to control each one with, and then we'll see a simplification. So I'll write down the final result to U, and then we'll argue for why it's true. So I'm going to have on the bottom the single qubit operation C. Then I'll do a controlled NOT. Then I will have on the bottom qubit the single qubit operation B, another CNOT, and then finally the operation A, and then the global phase. This is where we'll use the fun just matrix notation, 1, 0, 0, e to the I alpha. Okay. So this is the way that the textbook presents it. If there's any case where you don't want to give a name to a gate, like I guess here, then we could be creative with the notation. You can just use the matrix to represent that in the box in the circuit. So what happened here? There's a few things to note. First of all, in the formula, we're starting with A, and we go A, B, C. So why in the circuit am I starting with C and going C, B, A? Who can tell me? This is important. It's just a notational thing. When we do circuits, we start on the left, and then we go to the right. So if I had an initial state here, let's just call it psi. So we'll make the important note. I guess we would have seen this before, but this is the first time we're explicitly saying it. If I have some initial states, and I'm going through this circuit from left to right as we do, then I would apply the C operation. So C would be closest to the states. It would be on the right-hand side, right? And then I would do the NOT gate. It's going to be a controlled NOT gate, but so then it would be a C NOT, and then it would be CX, C psi. And so you see, if I do this again, then I would do the B gate. And so this is why. So this is the B. So B, CX, C psi. This is why the order gets reversed in the circuit. It's just the notation that we use. So sometimes this can be a little bit confusing or annoying. You just have to reason through it like this. Start on the left. The first operator you apply will be the one that appears on the rightmost side. So that's why the order is reversed. Okay? So that's an important note. Now let's see what's going on here. We need to argue that this is doing the circuit or the decomposition that we want. The NOT gates are controlled, right? But I didn't control the single qubit operations A, B, and C. You might think that that's not OK, but let's reason through what this is doing. So if this control qubit, and I'll have this be the target, if this control qubit is in the state 0, what does this entire circuit do? Who could tell me? Well, the first thing is that since C is 0, the CNOTs aren't going to do anything. Do you agree? So I can just ignore this CNOT, and I can ignore this CNOT. And then I'll have the product A times B times C. What do we know about the product A times B times C? It's identity. This is why we have this requirement here. Okay? And then the last thing you have is this phase rotation in the top left. This acting on the 0 states would just be 1 times the 0 state. Does everyone agree? So if C is equal to 0, final state of the circuit is 0. Well, 0, whatever the target qubit is. And that's what we want for the controlled U operation, right? Controlled U, if C is in the state 0, don't do anything. So we just do an identity circuit in that case. And so that's what we did here. Now, if C is in the 1 state, so if C is ket 1, then the CNOTs will be applied. The control qubit will not be affected by these CNOTs. Do you agree? When we do a CNOT, the control qubit doesn't change. I only change the target register. Again, we had this note, but in this case, we have basis states. So, I'm doing exactly the formula A times B times, A times X times B times X times C with the global phase, which I'll mention in a second. And so that's going to implement the formula that I want here. So if C is equal to 1, then we apply A, X, B, X, C, and then leave a note here to the target register T. And then the only thing that we have left is what exactly is going on with this single qubit rotation in the top right. Well, the sort of thing is, this is actually the controlled e to the I alpha gate. So let me show you why that is. So really what we did in the circuit was we went through and I controlled each of the operations. So I did a controlled C, controlled X, controlled B, controlled X, controlled A, and then controlled e to the I alpha. The order is reversed. We we discussed why that is. And then we saw the simplification that, well, if the control bit is 0, I actually don't need to control the single qubit operations A, B, and C. So we were able to remove those controls. And then the last controlled operation is this e to the I alpha. So let's see why that we can simplify this to be not a controlled operation. So we need to think about the controlled version of e to the I alpha. And it's implicit that there's an identity operation here. So we can say controlled e to the I alpha times identity. What would this be as a gate? Let's just use our definition. Projector onto the 0 state, tensor identity, plus projector onto the 1 state, tensor whatever the gate is. In this case, it's e to the I alpha times identity. Okay? So this is where we get to use the extremely trivial mathematical principle of the tensor product, where I can put this coefficient wherever I want. Okay, so it's surprising how simple this is, but the actual results that you get from it. So I'm just going to move this e to the I alpha to this other term in the tensor product. So I'll get 0, 0, tensor identity, plus e to the I alpha, 1, 1, tensor identity. Now the second term in the tensor product is identity for both. So I can factor that out. So this is 0, 0, plus e to the I alpha, 1, 1, tensor identity. Does everyone agree? Yeah, I just factored that out. And now look at this. Who could tell me what this gate is as a 2 by 2 matrix? It's exactly this matrix here, right? Does everyone see that? So this is 1, 0, 0, e to the I alpha, tensor identity. That's exactly the operation that we have on the last one in the circuit, right? So it's this matrix, tensor identity. Of course, that's implicit. So really, we're implementing the controlled e to the I alpha. And so we just went through this formula. We did the control of every operation using this principle. The control of a product is the product of controls. And then we simplified a few of the terms. We saw that we could remove the controls from A, B, and C. And we could also remove the control from this global phase. We just had to move it to this top and implement, top qubit and implement this gate. So that completes the proof of this. This is very nice now. We know that there's a way that I can do any controlled unitary U that I want, given only CNOT operations. And again, those are usually the only ones that I have available to me on a quantum computer. So this is a powerful thing. Usually the single qubit rotations will be arbitrary. You can just do any single qubit rotation that you want. The set of 2 qubit gates is a little more limited.